In our modern culture, we are obsessed with growth. It affects our investment decisions, as well as more niche examples such as the growth of populations or the spread of diseases. Understanding how populations grow is vitally important. For example, did you know Australia once fought and lost a war against an out-of-control population of emu? It's not so much of a stretch to make the link that understanding growth is fundamentally driven by mathematics. In this video, we are going to explore the mathematics that underpin the basics of modelling growth. Let's start very simple. We may have heard of the phrase exponential growth. This appears widely from the return on investments to the worrying spread of a global contagion. Even the aforementioned emu population could be represented as an exponentially growing population. It is based on the model developed by Thomas Malthus, an English economist most notable for his doomsday forecasting of population collapse. This model is as follows. It may seem daunting at first, so let's make it a little friendly by writing it out in words. The term on the left is population change, and it is equal to the product of the two terms on the right. The second term, n, is the current size of the population, and the first term, r, is the rate of growth. As either of these terms increase, the population change would also increase. So far, this does not link to exponential growth, so let's graph this. Looking at the graph, the population appears to increase unboundedly over time, and the population is growing faster. Now let's solve this. The solution can be written and expressed in simple terms as well. The population at some time t, written as nt, is equal to the population at some time point 0 multiplied by the exponential of the rate of growth times the difference in time. We can play around with the values of the inputs in this model. These are the population at time 0 and the growth rate. We can see if we start with a larger population, unsurprisingly it grows faster than a smaller population. Similarly, if we choose a larger value of r, the population grows faster, and if we choose a smaller value, it grows slower. Already we have arrived to a very useful model that is used excessively, but let's find some flaws in this model. Consider a population of emu out of control, such as those faced by Australia. If we use an exponential growth model, and let's say we start with 100 emu, and a growth rate of just 1, after the first year we would have 271 emu. In 2 years' time, that would be 739. In 10 years' time, that would be 2.2 million emu. But in 50 years is where it gets crazy. There would be more emu than grains of sand on all of the beaches on Earth. Clearly something is wrong. Since we know the world has not been, and does not appear like it would be, overrun by emu, clearly something is missing in this model. So let's propose a fix. There must be some cap to the size of the emu population. Populations in general cannot simply grow forever without limit. In the case of emu, the habitats are constrained by resources and space. In the case of a disease, its spread is constrained by the number of people to infect, and viral internet trends can only spread as far as the number of internet users. So let's explore our fix. Currently we have an exponentially growing population described by the previous equation. Let's give some credit to this model and say initially populations can appear to grow exponentially. This means we need to impose a manner of slowing down the growth so that it reaches a cap. We will call this cap the carrying capacity of a population, which is simply the maximum population size a particular environment can sustain. Let's call this k. As the population size approaches k, it should grow slower, and if it exceeds k, we should expect it to shrink. The model we explore is proposed by Pierre Velhurst. It is called the logistic growth model, and in this case, we multiply the exponential growth equation by the term 1 minus n over k. Velhurst proposed this to produce a more realistic model of the population growth of Belgium. Let's try to understand why. N over k tells us how much of the population capacity is saturated. It is the ratio of the population size to the maximum capacity. When the population is empty, this term is equal to 0, and when it is full, this term is equal to 1. We want our population growth to slow down as the population size approaches its limit. So we use 1 minus n over k. This is equal to 0 when the population is filled, and when multiplied to the exponential growth model results in a stable population. Now let's look at what happens under this model. We have a few parameters that we can change: the initial population size, the growth rate, as well as the new capacity term. If we start with a larger population now, it does initially grow faster, but they both arrive to the same maximum. This is similar with the change in the growth rate, they just arrive at different rates. The term k, however, allows for a change in the size of the maximum population. If we increase k, the size of the maximum population increases, and if we decrease it, the size decreases. This model solves our problem. The size of the emu population is now able to grow rapidly, but with an upper limit. The emu population cannot exceed that supported by the environment. These models explore the mathematics of population growth and represent a mere introduction into the world of growth modeling. This is Shrouded Science, where we explore hidden science that affects our everyday lives. If you enjoyed the video, consider giving a thumbs up and subscribing, and as always, thanks for watching.